take a one lecture. That's why, okay. Welcome to the micro communication course. Today we start here the new model, micro solid state devices, so in which we learn a tunnel diode. So earlier, if you compare micro tubes, so micro tubes in which interaction space and interaction region is there, and they are mostly depending upon that cathode and anode, and that tubes are used to amplify the micro signal as well as the generate a micro signal. Now here we have a solid state devices, and that solid state devices is used to amplify the micro signal, or that solid state devices is used to generate the micro signal. So that's why the name is about a microwave solid state device. Now various devices are there. We learn all the devices one by one and their applications. So where the solid state devices are used and what are the applications of this solid state devices, that we will learn. So before going into detail about all other diodes and all other diode families, so we start here with a topic of a tunnel diode. So all the solid state devices, most of the solid state devices, they work in a negative resistance region. Even this tunnel diode, even it will work in a negative resistance region. So just like we say that earlier a PN junction diode we supposed to see, and a tunnel diode is again, it is about a one kind of a PN junction there. Okay, tunnel diode is nothing but a one kind of a PN junction diode. But the impurities we are using in the particular junction diode, so based on that particular impurities, they have the various types of a diode here. That's why we start here a tunnel diode. So tunnel diode, if you see the characteristics, it is it has a heavily doped negative resistance. Okay, so we can say that, that's why we can say that this particular tunnel diode will be work in a negative resistance region. So we can say that it is about a heavily doped one. Okay, whatever the we have the PN junction, P or N, both are heavily doped here, and doping level in this case it is about a 10 to the 19 to 10 to the 20 atoms per second centimeter cube. Okay, not second, atoms per centimeter cube. That is about a doping. And because of that highly dopant region, so the junction we supposed to consider that a P N junction is about a diode now. It has a P and N junction. So this one at this particular junction, this P and N, this one region is called as the depletion region. And because of that heavily doped, but a heavily doped P and N is there, that depletion region width will be very very small. Okay, so that depletion region width for this tunnel diode is about a 100 angstrom. Okay, 100 angstrom means what? 10 to the power minus 8 centimeter. Okay, 10 to the power minus 8 centimeter. That is about angstrom. Even if you see that the unit that is used to measure the width, okay, so generally 10 to the power minus 8 centimeter, or 1 billionth of this, what you can say that meter there, or we can say that 100 picometer. Okay, likewise. So we are supposed to find out in terms of a meters, or in terms of a centimeter, or in terms of a nanometer there, so that particular length there. But here in the case of a tunnel diode, it is about a one, that is about 100 angstrom, or we supposed to say that 1 angstrom is about 10 to the power minus 8 centimeter. So these are the 100, so that's why it is about 10 to the power minus 6 centimeter. Okay, and that this we say that earlier this tunnel diode, it work in a negative resistance region, and this negative resistance region is produced by the This diode, because of there will be a tunneling action takes place at a junction. Tunneling action takes place at a junction means what? Whatever we supposed to say that a P and N here, so electrons will move toward the P. Okay, electrons will try to move from N to the P here. So that is about a tunneling of the electrons from the N to P here. But this one is about a field state. This one is about a empty state here. So electrons will try to move from this uh, from N to P here. And that motion of this, what we can say that electron from this N to P that occur or that process is called as a tunneling process there. So generally, if you consider that how this tunneling action takes place here for a given particular junction, so we should know that the behavior of a tunnel diode with respect to the energy band diagram. And again, we need to consider that tunneling action takes place at what value of the voltage. Okay, so we're supposed to be consider the some bias voltage is to be applied to the tunnel diode, and then we're supposed to find out that at what value of the bias voltage your tunneling action will be takes place here. So we see here first of all what will be the conditions when we say that a PN junction diode if we supposed to be apply the zero bias here. Zero bias means what? It is just like a open one. Okay, nothing is to be applied. It is just like a open one. So in that case, the barrier, this one is about a junction. Some junction has some particular potential. At this barrier, it has some particular potential. And that potential is depending upon that what material we are using. So generally, a germanium or a gallium arsenides are used in a tunnel diode. So we need to understand the tunneling effect here. So that's why we need to consider the energy diagram of a P-type material as well as a N-type material. So we consider that the condition, first condition is about a zero bias. Okay. So now in the zero bias condition, we're supposed to consider that the zero bias condition now. Okay, so this one is about, we have to talk about that this particular portion is about a P, this particular portion is about a N now. And we're supposed to say that, okay, so I just consider that this one. Now this one is about your valence band. Okay, we should know that what is the Fermi level. Okay, Fermi level, uh, or we should know that a what you can say that a Fermi band. Okay, so likewise, so we can say that we have the a Fermi level for this, and that is about EF is nothing but a Fermi level here, and then this one is about a valence band here. This one is about a EV here. This is right here. Okay, and then we have this forbidden band. This one is about what we can say that this one is about empty state. Okay, this one is about empty state. Here we have the AV. So we're supposed to say that this one is about a forbidden band here. Okay, and then we're supposed to consider that the another band is about a conduction band here. Okay, that's why we can say that we're supposed to consider that what will be the empty states and a filled state. So this one is about a filled state here. Okay, this one is about a filled state. Now we're supposed to write here the Fermi level EC. This one is about a EF here, and this particular band is called the conduction band here. And from this to this one is nothing but the energy gap. Okay, EG, and that is for the given conduction band here. Now these are about the a Fermi level here. Okay, so this one we say that a valence band. This one is about a valence band, and this one is supposed to be we say that's about a conduction band. Okay, this one is about a conduction band. Now, now we say that these are the levels that is about the EC. This one is about the AC is about the lower edge of the conduction band for the P here, and this EV, this one is about the upper edge of the valence band. This one is about valence band, but EV is about the upper edge of the valence band, and this EF is nothing but the Fermi level. So now from this Fermi level to this upper level of the valence band, this particular region we supposed to say that is about the empty state here. Now similarly here, we have the valence band here, and for this P band we say supposed to be this is about a gap, energy gap, and from this will be P, and from this will be AN. Now here we supposed to find out this gap or a gap voltage that is about a EG here, and this EV is about the highest value. EV is about the highest value of this valence band here in N region. AC is about the lower value of this uh, conduction band here, and EF is about a Fermi. Now, so you see that this one is about a Fermi level, and this one is about a Fermi level here. So Fermi level in both the cases, if there is a no bias, if there is a no bias, the Fermi level is at the same height. Okay. So in a zero bias condition, okay, this is about we can say that this PN junction we are not supplying anything. It is just like it acts as a open circuit. Okay, it will be act as the open circuit. So that is called as a zero bias equilibrium condition. So in this case, upper levels of the electrons of both the N and a p-type semiconductors are lined up at the same Fermi level. Okay, that's why we say that about a same Fermi level. And here we see that this one is about a filled state in okay, filled state here. Okay, and this one is about the empty energy state. Okay, so that's why you can say that about empty states or a filled energy state. This region is supposed to be called as a filled. Because of that, no bias is applied. So that's why no flow of a carrier takes place across this particular junction. And that's why no carrier takes because there is no bias. No electrons will be moved to this P here. Which no carrier is moving from this N junction N to the P here. No flow of a electrons there. That's why the no flow of a carrier takes. There is no if there is a no flow of a carrier means what? There is a no flow of a electron across, no flow of a current. So that's why the current flowing at the zero bias condition, it will be a zero there. Okay, so means across the junction, no flowing of the electrons will be takes place. So that's why there is a zero bias. If we consider that any diode, so for each and every diode, that Fermi level exists in the each and every diode there. But if supposed to be here, this tunnel diode, we supposed to be considered that it is about the heavily doped there. And because of that heavily doped there, so Fermi level will be at the same level. in the PN junction. And because of that heavy level again, the Fermi level is exists in the valence band in the P type conduction band here, as well as what you can say that we have the Fermi level at this particular N junction, both are at the equal level. Okay. If supposed to be, if we apply some particular bias, okay, instead of that, we say that zero bias. So instead of that, if we supposed to be applied some voltage, then the potential barrier will decrease. Why potential barrier decrease? Because of the applying the bias, that electrons will try to move from the N to P here. Okay, so that's why this particular barrier, that is about a fill state and empty state, we supposed to say that. So this and this Fermi level will change if we apply the bias. When we apply the bias, so the Fermi level will be increased here. So here, in this case, it will be here now if we apply the bias. And then at that particular point, the empty states and the filled state will be at the equal level. When that empty state and a filled state will be at equal level, then carriers will flow from this N state to the, sorry, from N to the P here. Okay, that will be moved from the N to P. So that movement of this particular carrier from this N to P here, so that is called as a tunneling action. So at what value of a bias voltage, tunneling action will be takes place from this particular carrier here. Okay, so that depending up that that is through that we supposed to find out that a VI characteristics of a tunnel diode. So if supposed to we say that, so now I am going to keep as it is this particular portion. I'm just going to change this particular portion. Okay. So now here, suppose if this one is about a zero bias condition. Okay, this one energy band diagram of a tunnel diode. So here we supposed to be considered at a zero bias. Now I consider that if the bias voltage is applied, it is a V now, but it is less than the Vp now. So in this case, what happens? Then a Fermi level, okay, everything will be changed. So what change occur here? Okay, so now what change occur? Now, because of that, whatever the expected Fermi level we supposed to be considered here, this one is about your EC now, and here we have supposed to be if EV now here, that is about a upper edge of the valence band. So Fermi level will reach to the upper end of the valence band. Why this gap? So this one is about a filled empty state and a filled state. Okay, this one is about empty. So that's why. So electrons will tunneling from this filled state to the empty state. So this one is about a tunneling action is detected. So in this case here, we're supposed to consider that there the here a barrier height is nothing but what, from conduction band to this one is about your a barrier height here. Okay, when we apply the bias here, when we apply the bias, so tunneling action will be takes place here. Then means there will be a flow of a carrier across the junction occur. This one is about a junction here. Okay, this one is about a junction. So flow of a carrier from this junction to this one occur, and that at that particular point, a tunneling action will be takes place. Means carriers will tunnel through this particular junction there. So that's why a current will start flow here. Okay, because of that, the current will start flowing here. If we further increase the bias, then again that Fermi level, or what we can say that The portion of that overlapping this empty states and this filled state will be overlap each other. So that's why a more tunneling will be takes place. So now again, this is about a condition here. This one is about a gap. So this one is about a empty state and a field. Now if you consider that another condition, that if V is equal to Vp, okay, if we consider that a V is equal to Vp now. So in that case, what happen? So this Fermi level will change. Okay. So this one is what happened here. So in that case, so this both the levels will be equal now. This empty state here and this one will be equal here. So in that case, this will be a AC and this will be a EF here. And then again, carrier will move again. So that's why if current is increases, we say that a tunnel current, that current is called as a tunnel current. When we apply the bias voltage, that will be the value of Vp here. So in that case, this gap will be here. A, the field energy state and the empty energy state. Field energy states and empty energy states both are at the same energy level. Okay, so this one. This one is about we supposed to be consider that this level. Okay, so this one we supposed to say that this is about a empty states and a field energy. Both are at the same energy level. And at this particular stage, because the energy state of the empty states and a field energy state here, both are at the same level. So that's why most of the carriers will move from tunneling to this junction here. So that's why there will be a maximum current is generated. Now, how our graphs will be looks like. Now here I am supposed to be draw a graph. So we supposed to be consider that a voltage here. This is supposed to be voltage and this is supposed to be current now. Now in this case, what happened? Generally, we supposed to be consider that the current will be increases and then at the Vp. So this is called as the Vp1. So it will be maximum at the Vp because empty state and filled state are of the same energy level. So that's why so current when we apply the bias, current increases because tunneling takes place. At some particular value of Vp here, so there will be a maximum current reach. And then if we further increase the bias, then current will be decreases. Now we talk about that particular portion. If supposed to be voltage will be applied voltage will be less, it is Vp. Okay, applied voltage is less greater than this whatever the Vp here. If it is greater than the Vp, so then in that case, so this Fermi level that is for the field state will be changed. So in that case, what will happen here? In this case here, okay, now this one there will be a gap here. Okay, this will be a gap. Only a small portion. This one is about a small portion. Will be at this level of this empty state. So that's why due to that only a small current will be flowing. Now here, so that's why after this Vp voltage, the current start decreases. After that Vp voltage, then current start decreases. Then again further, if we increase the voltage there, this one is about a Vv to the V to the infinite here. If we increase further this voltage, so then what happens? Then this particular band, okay, so we say that supposed to consider that empty state and this state here. So in this particular case, what happens? So this will be gap here. This one here we have the conduction band. This one is about a filled state and this will be about a. Now there will be a gap, like a small gap here in between the So that's why this Eg value and this Eg value will be a difference here. Okay, this Eg from this will be a difference here. So this one is about a conduction band. Okay, this one is about a conduction. Now here, what happened? So electron, that state will be increased. So that's why the tunneling action will not be takes place here. Okay, so means if we apply the bias, then there will be a overlap of this earlier state. We say that whatever the p side is there, that will be reduced. Okay, and even if we further increase the voltage, then at some particular point a negative resistance reach. Okay, this one we supposed to say that at the VV here. Okay, this one is about VV. If we increase further, so then diode will be act as a, what we can say that a, now if we apply further, if we apply the voltage further above this VV here, then whatever the negative resistance region we reach at this particular VV voltage, then again what happened? The energy of that field energy state on the N side, this one, that will be exceed the empty state on the P side. Okay, this one energy, so it will be increased, and that's why whatever we can say that earlier the carrier transfer takes place from this to this here. So that's why the diode will just behave like a normal PN junction, and a carrier transfer will be takes place in this particular case there, but only the action is about what, above that PV voltage. So just like a diode will behave like the a normal PN junction. So we need to find out here. So what will be the VI characteristics of this eternal? So now this one is about the energy band diagram. When we apply the bias and all, okay, and this one again will come back to this VI characteristics. Now and again another condition is about, this one is about a forward condition. So we need to talk about again the reverse bias condition. So in the reverse bias condition, what happened here? So this one is about the empty state. We're supposed to say that this one is about the empty state here. Okay. And this one is about the empty state. This one is about the empty now. Okay. And there is a small carriers are there. All this particular everything is about empty. But small carriers are there. And because of that reverse bias, so tunneling of those carriers will be takes place. Because of that reverse bias, a tunneling of those carriers will be takes place. And that carrier will be tunnel from this P to N. Carrier will be tunnel from the P to N. Okay. So this one is about a field state. This one is a field state. This one is about a empty state. So here from this electrons will tunnel from this P to N. Okay. Carriers will be in a reverse bias. When we apply the reverse bias, just like we have seen earlier, that is for the normal PN junction diode. So in this case of a reverse bias, so here we have some energy states are there in the valence band. So in that case, energy states are the same level. But only what happened here, this is about a, say AC, this is about a EF here, these are the Fermi level here. So electrons will tunnel through the barrier from the P to N here. And because of that, it will gives us the reverse current. So that's why we can say that in a reverse bias condition, we'll get that a reverse diode current. And in this case here, so tunnel diode will work because of this reverse bias apply. Because of this reverse bias when we apply, so then electrons will tunnel from this to this. So that's why there will be a reverse current occur. Now we talk about What will be the VI characteristics of this a tunnel diode? Generally, we have seen that a graph earlier. We have seen a graph of a tunnel diode in which we say that initially we supposed to consider some particular voltage, and at that some particular current a tunneling will be takes place. Now this one is about your IV. Now we say that this one is about your current I, and this one is about your voltage. Current start from 0 here, it will be increased some value. Okay, that is about a peak current. This one is about a IP. This is about a peak current. And then it will start decreases there. Then it will start decreases. Then it will reach to the region. Okay, it will reach to the region that is about a voltage. What we can say that is about a VV voltage. And this current at this peak here, that is about a VP now. Then it will start again likewise. So it will behave like a your PN junction. No need to draw okay large. Okay, in this region. So this one is about what we can say that AVI characters of this a diode. So now if you draw this VI character with in terms of a load line here, so there are the three load lines. First load line, so in that case, we're supposed to find out that the line it to be passing through the two components. Okay, so now this is about a point A, this is about a point B now, this one is about a point C. This one is about a first load line. Supposed to say that a first load line. So it will pass from the A, B and C. And then the second load line that will be passed through this point B. And a third load line that will be passed through this a point A. So we can find out a equivalent circuit for this what you can say that eternal diode here. So in that case, it has some a metal contact for the diode. So because of this uh, metal contact here, so there will be some resistance and there will be some inductance. Okay, sorry, that's about a resistance and inductance here. And we have the eternal diode. Because of that metal contact, there will be resistance and inductance. For the tunnel diode, we have the tuned circuit here. Okay, this one is about a tunnel diode circuit. This one we can say that is about R and this is about a C here. This one is about a Rn is nothing but a negative resistance at this tunnel diode. This one is about a junction capacitance. This Cj is the a junction capacitance there. And that junction capacitance is depending upon that how many number of electrons and hole concentration there, or we can say that how much is the dopant value. Okay, and it is again depending upon that a diffusion voltage there. And because of it, this ILS and RS is nothing but these are nothing but a packaging component, and this is nothing but your eternal diode component that is about a junction capacitor. And this LS and RSR belongs to the that is about a packaging component. So this way we can say that eternal diode is there. So and this one is about equivalent circuit of eternal diode. And generally, if you see the symbol of eternal diode, generally eternal diode symbol will be looks like here. We supposed to consider that a diode. This one is about a normal p-n junction diode, but eternal diode symbol will be it looks like here. So this one is about a eternal diode symbol. Okay, these are the lines here. Okay, so these are lines. So this one is about a symbol of the eternal diode. So generally, how your circuit will be looks like. If there will be a tunnel diode in any circuit, so in that case, we supposed to be consider that there will be resistor, there will be inductor, packaging resistors and inductor, and then we supposed to draw a tunnel diode there in the circuit here. Likewise, then we have the capacitive component parallel to this. Okay, likewise, we supposed to inductor and a resistor. So this one we supposed to be consider that a eternal diode. This one is about the symbol of a eternal diode. So where these tunnel diodes used? Tunnel diodes are used mostly in an amplifier. Then it is to be used in a mixer also. Okay, so we consider that a tunnel diode applications now. Tunnel diode is used in a amplifier. Okay, now we talk about the amplifier. In that case, it has a tuned circuit, then supposed to be a filter, then we we supposed to be consider the circulator here. Okay, this one is about a circulator. We have a port one, then another port is connected to the match load. This is about a port 4 here, and then it is to be connected to the internal diode. Internal diode is about a port 2 now, and then this one we supposed to get the output here. So now how this tunnel diode is used? So we have generally we supposed to consider that a tunnel diode is connected to the circulator here. We have seen the circulator here, and circulator is used to make the negative resistance amplifier. This one is about a negative resistance. And here we are supposed to consider the filter that is used for operating this particular amplifier in a given particular bandwidth there. And again, this filter is used for the matching the impedance with respect to the circulator there. Matching the impedance. Okay, so likewise, so matching the impedance. So now here input energy is input signal from the filter reach to the tunnel diode there. Okay, then tunnel diode will amplify the signal, and then amplified signal will provide the output to the port 3 here. This one is about a port 3. Then if supposed to be there is mismatch at this particular output, or if the tunnel diode will be amplified larger there, if any reflection occurs, so then that reflection will reach to the port 4 here. Some of the reflected signal reflected from the port 3 will be enters at the port 4 here. Okay, so likewise, you can say that from the port 4 here there will be a reflection. But here we supposed to be consider that a match load. So whatever the signals are reflected, that will be absorbed by this a match load. How it tunnel diode will work? How the circulator work? 1 to 2, 2 to 3, 3 to 4. If supposed to be any reflection come at this, then it will reach to the 1 again. Okay, so this way your circulator is used. Then a tunnel diode act as in a oscillator here, tunnel diode oscillator. So in that case, we supposed to be consider tunnel diode oscillator here. We supposed to be consider a cavity, and then through this cavity, we supposed to take the output. This one is about your probe now. Okay, take the output from the cavity now. This one is about a cavity here, and we supposed to change the cavity height and everything. That's why we have a tuner here. Tuner is to be placed here so that it will change the size of the cavity. So this one we supposed to be consider. Then we have tunnel diode circuit. This one is about a tunnel diode circuit here, and then we have the a cavity here. Now this one is about your tunnel diode. So now this one is a tuner. This one is whole is about a cavity. So generally tunnel diode is operating at a negative resonance region, and it is to be coupled with a tuning cavity. So in that case, a cavity behaves like a stable oscillator. Okay, cavity behaves like a stable oscillator, and that cavity frequency is equal to the frequency of a tuning circuit. So tuning circuit means nothing but what a tuned circuit has some particular resonance frequency. Okay, so generally tunnel diode is operating at a microwave frequency. So here we have the a cavity is there. Okay, and here we supposed to take out the output from the a given particular cavity. So tunnel diode here it is act as the oscillator here, and it will supply the power to the cavity. Okay, and then you can see that oscillation takes place, and will get take output from the a cavity there. Even a tunnel diode can be used as a mixer also. We can consider that a tunnel diode is to be used as a mixer, or we can say that tunnel diode can be used as a converter circuit, or generally we're supposed to consider that a tunnel diode is to be used in a switching circuit also because of the negative resistance region there. It is to be used for the amplification. It is to be used as a oscillator there. Okay, so these are about the applications of the tunnel diode. Then what are the frequency range here? So frequency range is about what? It will work up to a 100 gigahertz, and a output power supposed to be it is about a 700 watt, and tuning range is about 1 to 4.3 gigahertz. Now that's all about a tunnel diode here. So tunnel diode is to be used as a forward diode. So in that case, we supposed to find out that what will be the pinch of voltage, that is a P Vp here, and what will be the value voltage, that is a Vv there. So with respect to that, this one is about a pinch of voltage here. We will get the maximum, and then valley is about a Vv, that is about value voltage, and then it will behave like a normal diode. So that's all about a trail diode. So thank you all of you. Now